step response of RLC circuit. Step response of RLC circuit. So this will be your experiment number 5. Experiment number 5. Okay. So we'll consider an RLC circuit. RLC circuit. Impedance in S domain are also marked. Let the input be EI of S. Output be E0 of S, the voltage across the capacitor. Okay. So that will be, the current be I of S. I of S. Now I will write the KVL equation as EI of S is equal to I of S into R plus LS plus 1 by CS. Okay. What is E0 of S? E0 of S is equal to 1 by CS into I of S. Now transfer function is E0 of S by EI of S. So when you substitute for E0 of S and EI of S, you will get the transfer function as, in the standard form, as 1 by LC by S square plus R by L into S plus 1 by LC. So this is the standard form of the equation you are getting. You have to make the coefficient of S square unity. So when you make the coefficient of S square unity, you will get the standard form of transfer function as 1 by LC by S square plus R by L into S plus 1 by LC. So comparing with the standard form, so this is equal to, you can write with the standard form, omega n square by S square plus 2 delta omega n into S plus omega n square. So this is your standard form. So compare with the standard form. Comparing with the standard form, the numerator omega n square is equal to 1 by LC. So omega n is equal to 1 by root LC. R by L is equal to 2 delta omega n. And here for omega n you can substitute 1 by LC, 1 by root LC. So substituting you will get delta is equal to R by 2 into root of L by C. Delta is equal to R by 2 into root of C by L. Sorry, R by 2 into root of C by L. That is, when you substitute here for omega n, you will get the equation for delta. Delta is equal to R by 2 into root of C by L. That is the equation for delta in terms of the passive components R, L and C. And you can consider 3 cases: overdamped, underdamped and critically damped. So for overdamped you can choose delta greater than 0.1 greater than 1. For critically damped you can choose delta equal to 1. For underdamped you can choose delta less than 1, say 0.5. So for these 3 values, for example, put delta equal to 1, put C equal to 0.1 microfarad, put L is equal to 0.1 Henry, find R. Then come to the circuit. When you come to the circuit, you fix the value of R as we obtained from the calculation. You can put the L value as 0.1 Henry, keep the capacitor as 0.01 or 0.1 microfarad. And for delta is equal to 1, we have designed the circuit now. Apply a step input. What is a step input? Just you can use a function generator to apply a step input. So let the step value equal to some 10 volt. So this is the second order circuit and we have designed it for overdamped performance. So its performance will be like, overdamped. There will be no oscillations. And if you design the circuit for underdamped, it will be like this. Okay. So from this underdamped performance, you can measure the peak time, the rise time, the settling time, etc. Okay. So this is how you have to perform the experiment. So once you first of all write the transfer function, then from the comparing it with the standard form, find the value of obtain the formula for delta, that is R by 2 into root of C by L. Then for 3 different conditions of damping ratio, that is overdamped, critically damped and underdamped, find the value of R. So that C and L are already fixed. First fix C and L so that with the available values you have in the lab, and find the value of R for 3 different conditions of delta. Then perform the experiment by applying a step input at the input. Obtain the output, measure the output across the capacitor using a CRO and observe the waveform in the CRO itself. From the CRO you can measure the TP, TR as well as the peak value also. The maximum peak also you can. Okay, so this is how you have to perform the experiment and obtain the time domain specifications of step response. Means you have to obtain the time domain specification. Okay, thank you.